Example number 2 of the use of our equations of motion. Busted. So we got a story here. We have a police officer sitting at the origin. That's him in the dotted green line car there. Police officer sitting at the origin. Let me put a little siren on top of the car here. And you are driving your Porsche at 17.9 meters per second, which is 40 miles per hour, which doesn't seem bad, but you're in a school zone and the school speed limit is 25, so you are in deep trouble. Okay, so police officer sitting there just like they do up on Claremont, right north of downtown Decatur all the time. And I was busted there not long ago, well, a few years ago, for doing this very thing. So maybe it's me driving the sports car and not you, although I don't have the sports car. Got a Corolla. So, police officer sitting there, you go flying by at 40 miles per hour and you're going at a constant, I keep saying you, me, it's me, I'm breaking the law. I'm going at a constant velocity, and so my V is the same as my V naught, right? Because there's no change in velocity. In other words, acceleration is 0. I'm not accelerating. I'm just going at 40 miles per hour and keeping it right there at 40. Okay. I blow by the officer down there at the origin, and the officer, as soon as I pass, he's already read my time, and he's in his car. He's ready to go. And just as soon as I pass the officer, he takes off from rest after me. Okay. So my initial position is 0. Actually, let me do it this way for reasons you'll soon see. Hopefully you'll soon understand. Let me give it a little space here. My initial position, me, the speeder, my initial position is 0, and so is the police officer's initial position equal to 0. And we also know the police officer's initial velocity is equal to 0 because he's at rest, he's just getting in his car, he's going to come after me, okay? And when he gets in the car and takes off after me, he's going to be moving towards me at 4.51, accelerating at 4.51 meters per second squared. In other words, he's speeding up. Unlike me, my speed's not changing, my velocity's not changing, so I have 0 acceleration, even though I'm going plenty fast. My velocity is not changing, it's stuck at 40, so my acceleration is not happening. Okay? Not happening. Okay. And so eventually he's going to catch me, right? Because he keeps speeding up, speeding up, speeding up with this acceleration. And so the question is, what's the question? The question is, at what time does the officer catch up with me? And of course, what we're going to do is we're going to set T naught equal to 0. T is equal to 0 right there. So the T naught, as usual, is 0. So both of us, the clock starts at the same time that I pass the officer and he starts moving after me from rest. Okay. So what time, basically how long after I pass the officer is the officer going to catch up to me? Okay, so we know some stuff. Okay, we know some stuff right here. Which of these equations are we going to use? How are we going to show, how are we going to calculate a time that he catches me? Okay, whenever you have a situation like this of two different objects moving, you're going to have to use these equations twice. One for me and one for the officer. Okay, and I'm going to tell you now that the one to use is number 2. Okay, and in retrospect we'll go back and we'll see why that is. But we need to write equation number 2 for the officer and then for me separately, so let's do that. And what I want to do here, and this is why I left some spaces, is I want to put some additional subscripts on these. Now I've color coded it. You'll notice So all the green math corresponds to the officer, all the pink math corresponds to me in my fast car, right? Right? And also he's picking up a little bit too. So, but if we didn't have colors, we'd have to distinguish between my acceleration and his acceleration. So what we do, watch closely, is simply put, I'm going to put sub C for car on all of those. So we know that these numbers correspond to the car, and that these numbers here have a P because those apply to the police. Okay. So I want to write this out for the police officer first. We're going to use number 2. So X sub P equals X naught P plus V naught PT plus 1/2 APT squared. Okay. Now notice that the only quantity that never, the only symbol that never has a subscript is T, because T is the same for everybody. There's not, you know, a police officer's time and my time. We're all looking at the same clock here. There's only one time, and that time is going to be the same for me and for the officer. Okay. There's no subscripts on T. V has a subscript, right? Or sometimes has a subscript. And X sometimes has a subscript, but T is universal. Okay, so let's look at some of these numbers here. Let's do this really quickly. Not too quickly. I don't want to go through and confuse anybody. Let me find a good color here. Let's do blue. Okay, so the initial position of the police officer is 0. In other words, I can go through this now and figure out which one of these terms are going to be 0. And then we're going to do the same thing for me, for my sports car. Okay, so position of the police is not 0. I can see through this little window here. Position of the police is not 0, but the initial position was 0. So that is gone. What's the initial speed of the police, initial velocity of the police? That's right. It's also 0. So this term, because V naught P is 0, it doesn't matter what T is, right? If V naught P is 0, this whole thing is 0, so that term disappears. So what we have here is X sub P. These two terms go away. Is 1/2 AP T squared, where A sub P is the acceleration of the police. But we don't know the time, we don't know X sub P, we can't solve this for anything. What we need to do, though, is to do a similar, right, all of this is in green. It applies to the police officer. That's why all the subscripts have P's. We need to do the same thing now, but for me. So, car. Okay. We're going to write the same expression out. X sub C, the position of the car is equal to the initial position of the car plus V naught C times T plus 1/2 AC. Remember, all the C's and the subscripts were just added in to indicate whether we're talking about the car or talking about the police officer. Well, let's look at each one of these terms now and see what we get. Okay. What's the initial position of the car? Well, it's 0. The naught on the X sub X naught, that means the X at time T equals 0. That is at 0, as I said in the previous video, indicates T equals 0. So this X naught means the position at time T equals 0. Well, that was 0, as I have said right here. So that term is 0. What's the initial velocity of the car? Well, it's 40, right? I've been at 40 the whole time. right? I have zero acceleration, so my velocity remains constant. We don't know what that, well, we do know what that is. That's given to us, but it's not zero. But look, the last term, the acceleration term, is equal to zero because the car is not accelerating. So again, two terms equal zero, but they're different terms. For the police car, it was the first and second terms in the equation. For the car, the sports car, it's the first and third terms that are zero. So what we get here is x sub c is v naught c times time. Okay. Now, at what time does the car catch up with me? What time does the police officer catch up with me? Well, here's what you do. You ask yourself, what is true when the police officer catches me? What does it mean mathematically to say he's catching me? What does that mean? It means that the position of the car and the position of the police are the same. In other words, when he catches up, comma, what we have is we have xp equals xc. The position of the car, the sports car, me, and the position of the police officer are the same when the police officer catches me. That's what it means to catch me, that we have the same location on our number line when he finally catches up to me. And so we have xp here, we have xc there. We can set these two equal. xp equals xc, xp equals xc. But this is xp, this is xc, so those two things I just circled must be equal. Okay, I'm going to make this math blue now because I'm now blurring my two different colors together. Okay, so what I've got is xp is 1/2 ap t squared, right? That's xp, and then xc is v naught c t. We know everything but t. Right? We know a sub p is 4.51. We know v naught sub c, it is 17.9. So we can solve this for t. First thing to note is that we can divide both sides by t itself. What that does for us, and this is a nice little algebraic trick, it cancels both t's on the right-hand side, cancels one of the t's on the left-hand side, and so we're left with a very simple equation, 1/2 acceleration of the police car times time is v naught c. And so we can solve this for t, which is what we're looking for, right? Where's the question? At what time? That's what we're looking for. T. We solve this for t, and we'll get the time at which the two locations were equal when they met, when the police officer catches up with me. Okay, t, multiply both sides by 2, right? 2. That leads to a cancellation of the 2's on the left-hand side. Then divide both sides by AP, and you get 2 v naught c over AP, but we have numbers for these. We can now plug them in. 2, what is v naught c? Dang, 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 is 17.9 meters per second. That fit? Yes, that fits. Divided by a sub p, which is 4.51 meters per second squared. And and you find out that the cop car catches up with little old me, gives me a ticket, and it's very ugly, several $100s at least, at 7.94 seconds. So that's how long I have after I blow by the cop. Okay, before he catches up with me. Okay. Okay. This we can now find very easily how far it took for him to catch me. That is, at what location along the x-axis did he catch me? Now that we know t, right, we can very easily use these equations to find the position that he catches me. We can also find how fast he was going when he caught me. The textbook works out this example further. There's graphs and stuff. I encourage you to look at it because there's several more questions it asks, but this is the setup. And you can refer to your textbook for more details about the setup, and also, of course, as usual, I'm happy to answer questions during office hours and so forth and so on during work sessions. So that's it for today, and I'll see you next time. We'll move on to a very exciting development in one-dimensional motion. It's called free fall. See you then.